Alright, so in this new playlist, I'm gonna be talking about community detection, which is not specific to social networks. It could be protein networks, protein interaction. For example, a group of proteins are interacting with another group of proteins, or genes interacting with genes. It could be anything. Any graph could be represented like this, that inside each of these clusters we have a very dense graph, but among them, between them, there is some bottlenecks. So for example, in classical graph cut, we want to find such a good clustering, but also normalized. It means that for example, in each of these clusters, we don't want to have just only one node, but it should be normalized in terms of cardinality of the nodes inside each cluster as well. So this paper in 27 is very important, evaluating local community methods in network. Bagro. We present a new benchmarking procedure that is unambiguous and is specific to local community finding methods, allowing one to compare the accuracy of various methods. We apply this to new and existing algorithms. So you know that modularity is very important. This modularity objective is very important to find these community structures. For example, the first term, if you multiply this one and this term, then it's just a number of edges inside one of your clusters. The second term is just, if you multiply again with this, is expected number of edges, because these are just the degree of each node V and W. But this is a very global approach. There is a local community detection methods, in that we start with a single seed, and then we grow it so that it makes cluster. So for example, this one is a seed, we grow it and it becomes, so it's a local method. It's more practical if you work on networks, big networks. So we focus on efforts on two existing algorithms. So the clause that defines the following local modularity, and beta here is the adjacency matrix, comprising only those edges with one or more endpoints in C of border. So we have the community C, the set of nodes adjacent to the community B. So community C. So the set of all nodes that are adjacent, this is the border of that. So when we say B here, it makes sense that I and J should not be in the border. So at each step, the node with largest delta R is agglomerated, and it lies in this interval, as you see. But we define the number of edges, internal and external, to C. Because it's a local phenomenon, we start with a C, and we want to grow to see what is going outside, what is in the border, in this neighborhood. So it's a local phenomenon. And define the number of edges, internal and external, to C. And then this is the local modularity. In terms of inside and outside, the number of edges, internal and external, to C. For example, outside is in the cluster, one of the nodes, but the other nodes is in the border. Inside is both of those nodes are inside the cluster. So with this ratio in to out, we are talking about local modularity. I mean, everything is respect to C. So C is a weak community according to 10. And the algorithm consists of agglomerating every node in B that would cause an increase in M. So we present a new algorithm. So let us define the outwardness. This is the outwardness. Outwardness of C of a node V in B from community C. We want to know what is the outwardness of the community C. And this number of nodes is just, these are neighbors of node V. So here we are measuring the difference between them, the out and in. So the outwardness of a node is the number of neighbors outside the community minus the number inside, normalized with this degree, which is important. That's because it's fair if we normalize with that. Otherwise, it's not fair. It's a biased thing. And then we have this, that first they build a graph of M edges, perhaps using configuration model and a given degree distribution. Then we randomly partition the nodes of G into 2 or more groups. So it's random. These will serve as the actual communities, and we limit ourselves to 4 equally sized partitions. Choose a random pair of edges that are between the same 2 groups and rewire them to be within the groups. So if they are not, we rewire them to be in the same group. And this rewiring technique replacing edges with at different edges has been used to destroy the presence of community structure. Here we do the opposite, and communities become more sharply separated as the number of rewiring increases. So the modularity of the actual partition after T pairs of edges now becomes this. Alright, so that was the main idea of this paper.